Okay, we are doing nuclear in a day, last unit of the year. Woo! Last lecture of the year. I will never get up and teach you new material again. I know you're sad, unless you're taking organic next year then. Unless, unless I'm not here. Things happen in life. We never know. Never know. Anyway. All right, so I don't need you to know any of these nuclear stability rules. They're all rules of thumb. What I do want to focus on, though, is something called these transmutation reactions. These are your decay or decay and emission reactions. Sometimes these radioactive nucleotides can be absorbed, so they'll be on the left side of the equation, but for the most part, they'll be decay or emitted. The different types of emission particles you need to know are listed here. I want you to know alpha emission. An alpha particle is a 4/2 alpha. You're going to have to know these by heart, unfortunately. And what you'd have to do, the problem would say, uranium-238 undergoes alpha emission, and you have to write the equation. So start with uranium-238. You get your atomic number of 92 from the periodic table. You write down your alpha particle, 4/2 alpha, and then you say, okay, what do I add to 4 to get to 238? 234. Then you're like, what do I add to 2 to get to 92? 90. To identify what that is, you go take the 90, the atomic number, and find it on the chart, and that's where you get the TH. Okay, so you'll have to write those balanced equations. The alpha particles, skin pretty much stops them. They're super chill radiation. If you want to get hit by something, this is the one you want to get hit by. Okay. Again, you have to know it by heart. Next is the beta. It's kind of the same thing as an electron. Beta particles can make it into about 1 centimeter into the skin. It's 0/-1 beta. And you can see the math works the same way. Here, it is a negative, so you need to get 90. You'd need to have 91 over there. Gamma. Gamma is just energy. Its emission of energy is a form of light, so there are no values at 0, 0. So if you have an equation that is requiring gamma emission, you just write this on the end and tack it in, and it's usually coupled with one of the others. And this is the stuff that's in the X-rays. It's stronger than X-rays. This is stuff that concrete can't block. When we talk about nuclear fallout and going into shelters, it's because of this stuff. Next, you need to know what a positron is. A positron is a positively charged beta particle, 0/1. The positron itself can be emitted. A lot of times you'll hear about positron capture or absorption. So whenever they say something's absorbed or captured, you'd actually put it on the left side of the equation. If they say emitted or decay, it's on the right side of the equation. Two others I want you to know. I want you to know 1/1p. That's a proton. Protons can leave nucleuses too, nuclei as well. And a neutron, 0/1 neutron. Okay? We're going to practice these in a second, but one thing I want to bring up is our kinetics. We're going to revisit it because it's really important. Does anyone remember what I said about kinetics and radioactivity? First order. Okay? Everything we're doing in this unit, because they're nuclear reactions, are first order kinetics. So you're going to have to revisit the half-life equation. You've got to know the half-life equation for a first order reaction by heart. This is the first order integrated rate law. I prefer the way we did it in class and how we derived the line and everything. So you have to know it, but let's just use the version we're used to. ln of A minus ln of A naught is equal to negative KT. So recommit this to memory. It is on the AP equation sheet, but I still want you to know it because it's going to save you a lot of time. This is not on the AP equation sheet, so there's no option. You've got to know the half-life for a first order. While you're using it, a lot of times the question will be, after 25 years, how much of this isotope will be remaining if the half-life is 15 seconds? In a problem like that, you're solving for how much is left. You would be solving for this, okay? You don't know K. you know you're going for whatever I said, 30 years or whatever, you'd need this to find K first and then plug it in here. So that's the process usually. You're going to have to find K and then plug it into first order. All right. Let me make sure this is still blinking. Yes. Okay. Here's an example of doing one of these problems. I'm going to kind of work it on the side because they set it up and it rounds a little bit differently, and I don't like the way they set it up. So they're giving us carbon-14, and they're saying that the half-life of carbon-14 is 5,720 years. How old is something that has a carbon-14 to 12 ratio of 60%? So since this is radioactive, this is going to be a first-order equation, negative KT. They want to know how old something is. So what would that be for us solving for? What would we be solving for? Time. So we're looking for that. If 60% has been converted, we're going to assume 100. So this is 60. And what is this? 100. That's equal to negative. Well, do I know K? Because I'm trying to solve for T. No. So what do I do to find K? Do the half-life reaction. So T1 half is equal to 0.693 over K. And we know that our half-life is 5,720 years. So for the K, we get 1.212 times 10 to the negative 4. And we're going to take that K and plug it in here. So go ahead and do that and solve for your T. Okay, so the final answer, if you round to 3 sig figs based on the half-life having 3 sig figs, you should get 4220 years. One thing I was bad about, we always need units on K. So what were the units on K here? This is years. What were the K units? Not years. Come on, guys. Years to the... Okay, remember, we've got to have our units on K. And for first order, it's always whatever the unit of time is to the negative 1. Okay, a couple things we need to look at. The first is called, well, this is not called mass defect, but what we're looking at here is the loss of energy. In these nuclear reactions, energy is lost when decay occurs. It's kind of funky the way they set these up, but these are really grams per mole, first off. So what they did here was they found that when they did this reaction, mass was lost. This was actually 225.9971 grams per mole on this side. And this one was 221.9703 grams per mole on this side plus this 150. And when you do the math, you see that this is missing some mass, and that mass that it's missing is 0.0053 grams per mole. So the question is, what happened to that mass? It's coming off in the form of energy. So to complete the problem, what they did was they went ahead and took the missing mass, plugged it into equals mc squared. You can't see what that is. And whoever came up with these handouts did a crappy job because it needs to be squared, and y'all can calculate what the new answer is because it's not to the 8th. So someone figure out what that is. It's an error. But why did they have to convert it to kilograms? Why are we converting this to kilograms? Oh my gosh. Because we're solving for joules, the unit on the joules is kilograms meter squared over second squared. Because of that, you have to put kilograms into your E equals mc squared. In doing this, another error that's on this page, which frustrates me, AMUs up here aren't grams, they're grams per mole. So because this is really a gram per mole, this final unit is not a kilojoule, it's a, well, first of all, it should be a joule, not a kilojoule. Oh, that's what they did. They converted, I see. This is, the 8 is correct for kilojoules. It's not correct for joules, though. This is actually kilojoules per mole because of the fact that we have moles here. All right, so whenever we have missing mass, you're going to have to find how much energy is associated with that. So that's how much energy was given off when this reaction actually happened. Another thing I want to ask you, which is our next topic here, this should weigh, if I put it on an AMU scale, 226 AMUs, because there's 226 nucleotides in the nucleus, protons and neutrons worth. Why does it only weigh 225.997? Mass is lost holding it together. Why is mass lost holding together? What's that called? What is that mass? It's called the mass defect. But what's it called that's holding it together? Strong, it's similar, but that's not what we call it in chemistry. You did this last year. It's called binding energy. Does that sound familiar? That's the energy that's holding the protons together in the nucleus. Okay, so that's why this, a little bit of the mass had to be converted to energy to make that glue. Okay, so we're going to do the calculations in exactly the same way. Here we're calculating energy lost for an entire reaction, but we can also calculate binding energy by looking at an individual nucleus. So let's do that next. It says estimate nuclear binding energy. They give you the mass of a proton and a neutron. This is obviously wrong. What's wrong with this? And I did not type this out. This is from some other place. It's not grams. What is this? AMUs, which is also grams per mole. A mole of protons weighs 1, and a mole of neutrons weighs 1. So this is what an AMU is. Okay? There is a conversion between AMU and just straight up grams. Do y'all remember that? It's what's the weight of a proton? 1 AMU is equal to 1.66 times 10 to the negative 27 kilograms is equal to 1 AMU. Okay? So we'll actually do some practice problems here in a little bit, and I'll show you the differences between the problems. Nuclear fission, I want you to know that fission is breaking heavy nuclei. We specifically use uranium-235 in our bombs and in our, nuclear reactors, okay? And fusion, where does fusion occur? On the sun, and it's heavy hydrogen atoms coming together. Deuterium are hydrogen atoms that have 2 neutrons, not just 1, and they come together to make helium atoms, and super, super high activation energy to make it happen, but the amount of energy that comes off is redonkulous. Have yet to come up with cold fusion. Cold meaning not Antarctica, cold meaning just here, not on the sun. If that ever happens, our energy problems would be over. So let's practice. Alpha emission by antimony 121. So you need to find antimony on the table, and you're going to write SB. What's the atomic number of antimony? 51. And we're having alpha emission, so what are we going to write? 4/2 alpha plus, all right, what do we add to 4 to get to 121? What do we add to 2 to get to 51? 49. And what is that? IN. Okay. Be careful here. A proton is absorbed. So we have uranium-238. What's the atomic number of uranium? 92. If a proton is absorbed, what do? I add it, and I get 1/1p. So we end up with 239 plus, and what's the identity of 93? Okay. All right, alpha emission by aluminum-27. What's aluminum's atomic number? And we do alpha emission, 4/2 helium. So what do we add to 4 to get to 27? 23. And we add 11. And 11 is sodium. All right, beta emission by sulfur 32. Oh, what's a beta? Well, first of all, what's sulfur's 16, right? And then beta is negative 1b, 0 over negative 1b. So we have 32. What do we put on the bottom? And that is chlorine. Positron emission of arsenic 72. What's arsenic's 33? All right, and then we have positron, which is 0 over 1, 72 over 32. What is that? GE. Okay, got those? That's as far as you need to know on that. Let's work a math problem. It says polonium-210 radioactively decays by the emission of alpha particles. Its half-life is 138 days. Write out the decay equation. All right, what's the atomic number of polonium? How much? 84. And then emission alpha. So 206 over, what's 82? Lead. Calculate the rate constant for the decay. And by constant, I also need units. So what's the rate constant? T1/2 is equal to 0.693 over K. I know that the half-life is 138 days. And what is K? All right, what'd you say? 0.00502. And the units? 1 over days, or days to the negative 1. So the next question is, how long will it take before 5% of the original isotope remains? So that's how much is at the end. We assume 100, so what would our original amount be? 100. So ln of 5 minus ln of 100, it's a minus a naught being the original, equals negative K, 1 over days, times T, which we're going to solve for. And what unit will that be in? Days. How many days? Give me 1 sig, I guess. 6. Well, no, let's do 3 sig because the 138. 597 days. So y'all clear on this kind of problem? I don't really want to do the next one because it's the exact same. Use this equation, T1/2, and then plug into the thing a 10 minus 100. Okay? So I think you all know how to do this. This is all review from kinetics. What I really want to focus on here are these problems. Calculate the mass and energy change in joules. And I just want you to take off this when thorium undergoes alpha decay. Take off this 1 gram business. It's making it way too convoluted. Now, the fact we need joules is going to indicate something. First thing, though, I want to do is figure out how much mass is missing. We start with thorium, which is 229.9837, and these are the 2 products we produce. So to find missing mass, I'm going to take 229.9837, and I'm going to subtract my 4.00150, and then subtract my, I should do it out, 225.9771. So go ahead and give me my missing mass. .0051. What's the unit on all this stuff that they have up there? AMUs. So this is AMUs. So now what we have to do, it says calculate the mass loss. There's our mass lost. and the energy change in joules. So this is where students get really, really confused with, do I use AMUs? Do I go to kilograms? Do I do grams per mole? They never know what to do. So let's talk about this for a second. E equals mc squared. I just want joules as my answer, not joules per mole, just joules. So if I just want joules, I need my unit to be what? Kilograms meters squared over seconds squared, right? So I want kilograms here. That's it. That's all I want there is kilograms. Not grams per mole converted to kilograms per mole, just kilograms. So what do I do to get kilograms? I use that factor that we just mentioned earlier, that for every 1 AMU, I have 1.66 or 7. 67? 1.67 times 10 to the negative 27th kilograms. All right, so go to 3 sig figs. Go ahead and give me the kilograms, please. 8.52 times 10 to the negative 30th kilograms. Well, there it is. So now what we can do is plug just those kilograms in times the speed of light squared and solve. So E is equal to 8.52 times 10 to the negative 30th kilograms times 3E8 meters per second squared. So that'll give me an energy just in joules. What do we get? Can I get a second on that? It is Jasmina, you know. Oh, so she's going for a right record, a B right record. Okay, so that's one way to find joules of energy loss. What I want to look at now, let's go ahead. Are you okay with just not doing any more of these? I really think you guys can handle this stuff. This is SoChem 1. This is the one. No, do I want to do this one? These are more joules given off of full reactions. I want to look at some more. So we already did one like this. I want to look at some more that are on the actual level of the nucleus. Let's go to this problem. Calculate the mass deficiency for chlorine-35 atoms. The actual mass of chloride-35 atoms is 34.9689 AMUs. All right, so chlorine-35 should really weigh how many AMUs? 35 AMUs. It actually weighs 34.9689, and the thing is going crazy. So go ahead and subtract that for me and get the mass defect. Oh, come on. Okay, 0.0311 is what you get as the mass defect after you subtract these. And the unit on this is AMUs. So that's the mass defect. Okay, it doesn't specify if they want it in kilograms or not. So we're done with that one. So just remember this number, because the next thing then is calculate the binding energy. So what was that AMU value? 0.0311 AMUs. Now here's the difference between the last problem and this problem. In the last problem it said calculate the energy lost in just joules. This is wanting binding energy in joules per mole. Okay, so we need a per mole aspect to this. In our E equals mc squared, in order to get joules per mole here, we need kilograms per mole there. Do y'all see that? If I need joules per mole here, I need kilograms per mole there. Since I need kilograms per mole here, look back at the AMU. What is an AMU? What grams per mole? So all I have to do to get kilograms per mole is divide that by 1,000. 0.00031. Can we make this easier? 3.11 times 10 to the negative fifth? Okay. So that's how many kilograms per mole we have. So that we can just plug directly in. We don't have to convert. So do y'all see the difference between the two types of problems? All right, so let's plug in. I'm going to use a different color. We want energy in joules per mole. Our mass is 3.11 times 10 to the negative fifth kilograms per mole. C is 3e8 meters per second squared. So what is the energy holding that nucleus together? Okay, and the unit, joules per mole. Okay, so there's a difference there. I need y'all to be aware of that difference. Okay, let's look at some more radioactive stuff. I'm going to show you two ways to do this. First, the way you already learned, and that's probably the way you'll want to stick with, but I will show you a shortcut. So it says cobalt treatments used in medicine help stop certain types of cancer. Cobalt-60 decays with the emission of beta particles and gamma rays with a half-life of 5.27 years. How much of a 3.42, and this is a microgram. It looks like a little U with a fancy U. When a 3.42 microgram sample of cobalt-60 remains after 30 years. So it's interesting if you get chemo or you get certain types of radiation, how long that stuff sticks around. So that's what we're going to figure out. Since this is radioactive and it's a nuclear situation, A minus A naught equals negative KT. I know this is going to be going for 30 years, so I'm going to put my 30 in there for time. What else do I know? I want to know how much is left, right? So I'm solving for that ln of A. How much do I start with? 3.42. You can leave it in micrograms. Just know that when you solve for this A, it's also going to be in micrograms. Uh-oh. What do I need? I need K. So how do I get K? Half-life equation. T1/2 is equal to 0.693 over K. 0.693 divided by 5.27 years is equal to 0.693 over K. What'd you get for K? 0.131 years to the negative 1. So that's what I'll put in here. 0.131. Okay, I have 0.131 years to the negative 1. Those years cancel, leaving me with micrograms as my answer. What did you get? 0.0662? 0.0662 what's? Micrograms. So even after 30 years, you still got some left. It's pretty crazy. Now let me just show you the quick way you could do problems like this. I think it's still better to do it this way, but in a pinch, anytime you're doing any sort of problem, they want to know how much is left after a certain amount of time. The amount left is equal to the original amount times 1/2 raised to the number of half-lives. Okay? So if I know that I'm going for 30 years, and I know each half-life is 5.27 years, how many half-lives is that? Just divide them. My original amount is 3.42. Did anyone figure that out yet? How many half-lives? Carry it out a little more. 5.6926. Okay, so if you solve this, you're going to get close. There's going to be a rounding difference, but you're going to get pretty close. What do you get when you solve for it that way? 0.0661. So whichever way you want to do it, you can. But that's a good little equation sometimes to have in your pocket. Original amount times 1/2 raised to the number of half-lives, which makes sense. After 1 half-life, you're splitting the original amount in half, right? After 2, you're splitting it in fourths, and that's that squared, and so on and so forth. So it makes sense logarithmically. So we're going to get rid of this last problem because we're going to end the year with another. You're not done yet because I'm going to give you a problem based on a true life demo story. We're ending our lectures with the infamous spider story. You ready? I've never recorded this story before because it's really hard. Okay. So in college, I was a resident assistant. It was a summer. I'm not going to tell you the year. That's not important. I was a resident, an RA in consulting. I don't know if any of you are familiar with the dorms at UT. And it was summertime. You know, class loads are pretty light. And we were hanging out. Consulting has 2 towers. And then there's a building that's shorter in the middle. That building, you can go on top on the roof and play volleyball and barbecue and all sorts of stuff. So we were playing volleyball one afternoon. And I remember it was around noon. And I remember something hurting when I was playing, but I kind of ignored it. And so we were done around 1 o'clock, went down to watch movies, and I look, and I had this black circle on my arm. And you could see like bite in the circle, so I apparently had been bit by something. But it was really, really dark and black, and it looked like venom or whatever was being pulled down by gravity down my arm. And people were freaking out, oh my God, you got bit by something bad, that kind of thing. So I went to the infirmary right across the street. And the doctor there said, new doctor, fresh out of med school. I think that's the only job she could find. Said, hey, you've been bit by a brown recluse spider. I need to give you this drug called dapsone. Never given it before. Used to be used on people with leprosy. So all this stuff is making me feel really good about this whole thing. And I can't remember the dosage, but there were teeny tablets. And it was supposed to be 15 milligrams every 8 hours, I think. And she goes, I'm not familiar with this. Let's just start slow. Just take 1 tablet, which is 5 milligrams. Just take 1 tablet. We'll see how it goes, and we'll talk later in the next few days. And so got back to the dorm, took the tablet. By this time it was like 3 or so. So hung out, kind of fell asleep, I remember. I woke up to go to dinner, and I had a headache. I remember going, oh, I don't feel good. But I was like, maybe I'm hungry. So I went down to the cafeteria, and this guy that was a friend that I had a crush on, really, I'm not going to say his name just in case. I still don't want him to know, even though he's a doctor somewhere else. He was like, were you drinking grape knee-high? And I was like, no. And he goes, your tongue is purple, and your lips are purple. And I was like, what? So, and I was feeling bad. I was like getting this headache. And sure enough, I looked in the mirror, my gums were almost like deep violet purple, and my tongue was getting purple. And then I went upstairs, and I had nail polish on. I went upstairs, took my shoes off, my toenail beds, and I knew that that's that's an oxygen thing. I knew enough about science to know that this wasn't a good thing. So I called the bells. Oh, we got time. I called the nurse in the quack shack, and I was like, "Hey, lady, nurse lady, this is the situation." So I hear her open up this book and flip through pages. She says, "Oh, cyanosis is a normal side effect. Blah blah blah." That's what it's called when you lack of oxygen, cyanosis. So don't worry, just stop taking the drug and go see your doctor tomorrow. I was like, okay. So I stopped. I didn't take any more. I never took anything but that 1 pill. And as the night wore on, I got so sick. My gums got darker. I actually started getting yellow, was getting really jaundiced. And the headache that I had, I was to the point I couldn't even get up because the light, I mean, I had the worst headache I've ever had in my life. I was sick. I was on occasion throwing up. I was just sick. Something was really, really wrong. So 6 a.m. came. My friends in the hall helped me to the infirmary. We kind of busted it on the doctor, and the doctor's like, holy crap, why didn't you come in sooner? Because your nurse told me not to. But anyway, she immediately admitted me. It turned out the drug converted hemoglobin in my blood to what's a natural occurring thing called methemoglobin. But most of us only have a few hundredths of a percent of our blood doing this. It does it naturally. But this converted, by the time they tested me, which was probably a lot had already gone away, I was at 35% of my blood was methemoglobin. So oxygen, when it turns the hemoglobin to methemoglobin, it just kinks it. Oxygen can't fit into the hole, into the heme. So oxygen was just not processing. So all the oxygen they were giving me, none of it was working. And this took forever for them to figure out what was going on. And so it turns out this was an enzyme deficiency that I had. And the lady was like, well, it's usually, research is saying it's Mediterranean based. Like, I'm like, well, my dad's from Naples. So he probably had it too. So anyway, they finally decided just to let the methemoglobin go back and just to bear through it. I was already as bad as I was going to get. They were worried about my liver and stuff, but they were watching me because the yellow was jaundice. I was bordering on liver failure. Like I was that sick. So anyway, they let the hemoglobin turn back. I was at, write this down. Here's your question. Here's the point. The half-life of methemoglobin is 17 hours. My blood was 35% methemoglobin, and they wouldn't let me go until I was under 2%. I stayed a lot longer than this tells you, but how long mathematically did I stay in that hospital? Figure it out. I'm going to pause the video. So 70 hours, how many days is that? Three-ish days. Okay. And here's the sad part, here's the scary part of the story. What would have happened to Demo had the doctor given the prescribed dosage, that 3 tablets? Dead. Absolutely. Dead before nightfall. That's scary. But it's scary. I'm alive. What's scary is how we blindly just do what the doctors tell us. Really, I didn't know I had that allergy. They didn't know I had that allergy. Less than 1% of the world's population has that. It's not an allergy. It's an enzyme deficiency that I have. Less than 1% of the world's population has that. So they didn't expect it. It's nobody's fault, but just be careful before you take drugs. Think before you do. Demo, life lessons. That's a good way to end our lectures this year.